Dear students, let us continue with our discussion on refrigeration and air conditioning. So, last class we were discussing about Carnot heat engine. So, last class we tried to relate Carnot cycle with our modern refrigerator. So, in order to understand our modern day refrigerator, we were trying to incorporate our Carnot cycle. So before we moved on to our Carnot refrigerator, we studied about the Carnot heat engine. So we related it with the working of our automobile engine, and we were discussing about that cycle. So Carnot heat engine is nothing but which will be receiving heat which will be receiving heat from a high temperature source during this process 2 to 3, and it will be doing some work, for example moving of our crankshaft in an automobile like that, and thereby pushing the automobile forward, and thereby thereafter rejecting heat to a low temperature sink. So that is where what we were discussing last class. So we studied about the TS diagrams, and we tried we have derived the uh, uh, heat engine analysis, and we derived the efficiency of the Carnot heat engine as 1 minus T1 by T2, where T1 is the temperature of the surroundings, or the low temperature surroundings, and T2 is the temperature at which the engine receives heat from a high temperature source. So the high temperature source temperature is that T2. Next, we will try to discuss our Carnot refrigerator. Carnot refrigerator. So refrigerator, as we have discussed in the last two classes, is nothing but which will be transferring heat from a low temperature source to a high temperature sink. ഈ പേരുകൾ കേട്ടൊന്നും പേടിക്കേണ്ട കാര്യമില്ല. Low temperature source is nothing but a region where a low temperature needs to be maintained. For example, the freezer compartment of our refrigerator, or the freezer compartment of an ice cream chamber. നമ്മൾ ഒരു ഐസ്ക്രീം നമ്മൾ കീപ്പ് ചെയ്യണം. ഐസ്ക്രീം കീപ്പ് ചെയ്യണമെങ്കിൽ നമ്മൾ ഒരു ലോ ടെമ്പറേച്ചർ ഒരു റീജിയൻ കീപ്പ് ചെയ്യണം. സോ വി ആർ ഗോയിങ് ടു ട്രാൻസ്ഫർ so in thermodynamics, source is nothing but the region where we are absorbing heat. Then this refrigerator will be absorbing heat from this low temperature source, for example, the freezer compartment of our refrigerator, and it will be rejecting the heat to the surrounding atmosphere. And normally the surrounding atmosphere will be at a higher temperature compared to our freezer compartment. അത് നമുക്ക് എല്ലാവർക്കും അറിയാവുന്നതാണ്. നമ്മുടെ ഹൗസ് ഹോൾഡ് റെഫ്രിജറേറ്റർ എടുത്തു കഴിഞ്ഞാൽ തന്നെ ഫ്രീസർ കമ്പാർട്ട്മെന്റ് ആയിരിക്കും നമ്മുടെ കിച്ചണിലുള്ള അറ്റ്മോസ്ഫിയറിക് എയറിനേക്കാളും കുറഞ്ഞ ടെമ്പറേച്ചറിൽ ഇരിക്കും. സോ വി ആർ ഗോയിങ് ടു റിജക്ട് ദാറ്റ് ഹീറ്റ് ടു എ ഹൈ ടെമ്പറേച്ചർ സിങ്ക്. Sink is nothing but it is referring to that is especially in thermodynamics, the term sink means the region to where we are rejecting the heat. ആ ഒരു ഐഡിയയിലാണ് ഇതിനെ ഹൈ ടെമ്പറേച്ചർ സിങ്ക് എന്ന് പറയുന്നത്. So here if we are representing it in on a diagram, നമ്മൾ ഡിസ്കസ് ചെയ്തായിരുന്നു as a mechanical engineer, we will be first describing a device or a system using a meaningful diagram. So that is what is done over here. Okay, so here what the refrigerator is doing is especially in the freezer compartment, the freezer compartment process is shown over here from 4 to 1. So heat from a low temperature source, for example the freezer compartment we may have kept some meat or fish or ice creams or some medicines in the freezer compartment. The heat from those sources, that is heat from that low temperature source, will be absorbed by the working fluid in the freezer compartment 4 to 1. Then it is having a very low energy, that working fluid. It has to reject the heat to our surroundings, which is at a higher temperature. So this working fluid needs more energy than it presently have when it is at the freezer compartment. So we will be doing work, or we will be energizing, or we will be pressurizing, or we will be applying some additional energy to that working fluid by means of a compressor. So thermodynamically, compressor is a term denoting where we are supplying energy or work, or whenever we are doing whenever we are supplying external work or energies to a system. So compressor എന്നുള്ള ടേമാണ് നമ്മൾ ഇവിടെ യൂസ് ചെയ്യുന്നത്. സോ when you look at when you get a chance, you look please have a look at all the components of our household refrigerator. There you can see a particular portion where it is producing a humming sound. That is nothing but the compressor, and that compressor is doing this work. That is, it will be energizing this working fluid, which have already taken the heat from our freezer compartment. Then in order to make that working fluid reach a level where it can reject the heat to a high temperature sink, that is our surroundings, it needs more energy. And that energy, extra energy, is supplied by doing work by means of this compressor. So 1 to 2 is normally the reversible adiabatic compression. So um, so 4 to 1 is the refrigeration step. 4 to 1 is the refrigeration step, that is the reversible isothermal heat addition. So thermodynamics heat addition or heat absorption വളരെ ഈസി ആയിട്ട് റെപ്രസെന്റ് ചെയ്യുന്ന ഒരു പ്രോസസ്സാണ് ഐസോതെർമൽ. അതായത് കോൺസ്റ്റന്റ് ടെമ്പറേച്ചറിലാണ് ഹീറ്റ് അഡീഷൻ അല്ലെങ്കിൽ ഹീറ്റ് റിജക്ഷൻ നടക്കാനുള്ള ഏറ്റവും എളുപ്പമാർഗം. അപ്പോൾ വളരെ എളുപ്പത്തിലുള്ള ഒരു അസംഷനാണ്. We are assuming that this heat addition is happening in isothermal process. So when we are discussing a practical refrigerator or a real refrigerator, this may not be the case. This purely isothermal heat addition process is not possible practically. But now we are slowly moving on. We are now in the introduction stage of our refrigeration air conditioner subject. So here we are assuming certain things as an introduction. So here we are assuming that this heat addition is happening in isothermal process. Then this compressor work also, that is work addition. Here we are discussing thermodynamically. It is very easy to assume such a work addition process as adiabatic, and we are assuming it as a reversible adiabatic, which will be nothing but isentropic compression. So we can represent this 4 to 1 and 1 to 2 as 4 to 1. It is we are assuming it as a isothermal or constant temperature process. So in a TS, temperature versus entropy diagram, where we are taking temperature along y-axis and entropy along the x-axis, the 4 to 1 process will be a horizontal line. Then 1 to 2 will be a vertical line, because here we are assuming this work done by the compressor as reversible adiabatic or isentropic constant entropy process, or constant entropy compression. Then after getting the sufficient energy from this compressor work, now our working fluid is having is having sufficient energy so that it can reject the heat to the surroundings, or to our the surrounding atmospheric air which is present in the kitchen. So for example, when we are taking the case of a household refrigerator or a kitchen refrigerator, we will be keeping that refrigerator inside the kitchen. So what the refrigerator is doing, the refrigerator will be absorbing heat from a low temperature source, for example our freezer. It will be getting additional energy from the compressor. Then it will be in a position to reject the heat to the surroundings. In the case of a household or kitchen refrigerator, the surroundings means it will be a high temperature. It will be the surrounding atmospheric air which will be surrounding the refrigerator, and at the same time it will be at a higher temperature than or compared to our freezer compartment. So here the arrow shows away from the system, which means heat is rejected to the high temperature sink, for example our surroundings itself. So now the working fluid has rejected the heat. It has lost or its energy is getting reduced. But it will be at a higher pressure now, because when we are doing work by means of a compressor, the working fluid will be at a very highly pressurized stage. At this pressure, if we are admitting our working fluid directly to our freezer compartment, there may be a chance that the freezer compartment or the side walls of the freezer compartment may burst. അതായത് നമ്മൾ ഈ കംപ്രസർ വർക്ക് കാരണം നമ്മുടെ വർക്കിംഗ് ഫ്ലൂയിഡിന് ഹൈ പ്രഷറിലായിരിക്കും നിലനിൽക്കുന്നത്. ഈ ഹയർ പ്രഷറിൽ തന്നെ ആയിരിക്കും ഈ ഹീറ്റ് റിജക്ട് ചെയ്ത് കഴിഞ്ഞാലും അതിന്റെ കണ്ടീഷൻ. അപ്പോൾ ഹൈ പ്രഷറിൽ ഇരിക്കുന്ന നമ്മുടെ വർക്കിംഗ് ഫ്ലൂയിഡ് നമ്മൾ തിരിച്ച് ഡയറക്റ്റ് ആയിട്ട് നമ്മൾ ഫ്രീസർ കമ്പാർട്ട്മെന്റിലേക്ക് അഡ്മിറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ ഫ്രീസർ കമ്പാർട്ട്മെന്റ് ചിലപ്പോൾ പൊട്ടിത്തെറിക്കാൻ ചാൻസ് ഉണ്ട്. അവർ ഫ്രീസർ കമ്പാർട്ട്മെന്റ് മേ burst due to the high pressure. So we need to reduce the pressure of our working fluid before it is admitted to the freezer compartment again. ഇതൊരു സൈക്ലിക് പ്രോസസ് ആണ്. ഇത് ഹീറ്റ് റിജക്ട് ചെയ്തതിന് ശേഷം ഇത് വീണ്ടും ഈ വർക്കിംഗ് ഫ്ലൂയിഡ് ഫ്രീസർ കമ്പാർട്ട്മെന്റിൽ കയറിയാൽ മാത്രമേ കണ്ടിന്യൂസ് ആയിട്ട് ഈ ഫ്രീസർ കമ്പാർട്ട്മെന്റിൽ നിന്ന് ഇങ്ങനെ ഹീറ്റ് റിജക്ട് ചെയ്ത് അല്ല ഹീറ്റ് അബ്സോർബ് ചെയ്ത് നമുക്ക് പുറത്തേക്ക് റിജക്ട് ചെയ്യാൻ പറ്റുള്ളൂ. So this is a cyclic process. So in order to reduce the pressure pressure of the working fluid, even after rejecting heat to the surroundings, we have to bring down its pressure. Okay, so bringing down the pressure of a system or a fluid is thermodynamically represented as turbine. നമുക്കറിയാം ടർബൈൻ ഈസ് എ എനർജി അബ്സോർബിംഗ് ഡിവൈസ്, അത് നമുക്കറിയാം. സോ thermodynamically, whenever we want to reduce the energy or a pressure of a system or a fluid or a working fluid, we just need to pass that fluid through a turbine. നമുക്കറിയാം ഹൗസ് ഹോൾഡ് റെഫ്രിജറേറ്ററിലൊന്നും ഇങ്ങനെ ഒരു ഫുൾ ഫ്ലച്ച്ഡ് ടർബൈൻ ഒന്നും ഇല്ല എന്ന് നമുക്കറിയാം. സോ there will be some provision in our household refrigerator where there is a chance for pressure reduction. Okay, so that is done by means of a pressure reducing valve. So we'll be learning more about it in our coming sessions. So 223 is our heat rejection happening to our heat is getting rejected to the surroundings. So again, heat rejection or heat removal, again we are assuming it as a isothermal or constant temperature constant temperature process. We are assuming it as a reversible isothermal heat rejection process to a high temperature sink, for example surroundings. So 223 can be considered or represented as a horizontal line again in our TS diagram. So 4 to 1 already consider ചെയ്തു, 1 to 2 ഇപ്പോൾ consider ചെയ്തു, 2 to 3 ഇപ്പോൾ നമ്മൾ consider ചെയ്തു. So then 3 to 4 we are assuming it as again pressure rise or pressurizing the working fluid was done by the compressor work. Compressor work was assumed as a reversible adiabatic. So pressure reduction or expansion, it will be the opposite of compression process. Again we are assuming it as reversible adiabatic expansion process. So reversible adiabatic means it will be a isentropic or constant entropy process. So we can represent it as 3 to 4. Then some important notes, that is the process 4 to 1 is the refrigeration step, means removal of heat from a low temperature source, example freezer of our refrigerator. This is the entire purpose of this cycle. നമ്മളൊരു റെഫ്രിജറേറ്റർ വർക്ക് ചെയ്യുമ്പോൾ അതിനകത്ത് ഏറ്റവും ഇമ്പോർട്ടൻ്റ് വർക്ക് അല്ലെങ്കിൽ ഇതിനകത്ത് ഏറ്റവും ഇമ്പോർട്ടൻ്റ് വർക്കിംഗ് പോർഷൻ ഏതെന്ന് വെച്ച് കഴിഞ്ഞാൽ റെഫ്രിജറേഷൻ സ്റ്റെപ്പ് ഓർ അവർ ഫ്രീസർ കമ്പാർട്ട്മെന്റ് വർക്കിംഗ്. സോ 4 to 1 പ്രോസസ്സ് മാത്രം മതി ശരിക്കും ഒരു റെഫ്രിജറേറ്റർ വർക്ക് ചെയ്യാൻ. ഓൾ ദ അതർ പ്രോസസ്സസ് are acting as a supporting system which will be helping to discharge this low temperature energy to some convenient high temperature sink. Okay, so 4 to 1 matram, it will not stand, it will not stand alone, but the other process like 1 to 2, 2 to 3, and 3 to 4, they are the supporting mechanism to carry out the main or important step, that is the 4 to 1. Example of a low temperature source can be the freezer compartment of our refrigerator. Example of a high temperature sink, it is nothing but the surroundings. Okay, then till now we were calling the working fluid simply as working fluid. Okay, working fluid is nothing but which will be working fluid is nothing but which will be absorbing heat from a low temperature source, and this working fluid is getting compressed by the compressor, and now this working fluid is rejecting the heat to a our surroundings. So now we will be giving a name to the working fluid in a refrigeration cycle, which is nothing but refrigerant. So from now on we will be calling the working fluid in a refrigeration system or cycle as refrigerant. Refrigerant എന്നുള്ള പേര് നിങ്ങൾ ഓൾറെഡി കേട്ട് കഴിഞ്ഞ് കാണും. CFCs, carbon, chlorofluorocarbons, that is this some we have already learned about some environmental effects of this rejected refrigerators, that is due to the refrigerant leak happening from the discarded refrigerators. The refrigerants normally may be containing some chlorofluorocarbons, which if coming outside to the atmosphere, it may cause ozone layer depletion. ഇതെല്ലാം നമ്മൾ ഗ്രീൻ ഹൗസ് എഫക്റ്റ് എന്നൊക്കെ പറയുന്നത് നമ്മൾ ജൂനിയർ ക്ലാസ്സിലൊക്കെ പഠിച്ചിട്ടുള്ളതാണ്. So refrigerant is nothing but the working fluid which is doing all the work in our refrigeration cycle. So till now we were discussing about the Carnot refrigeration cycle or the Carnot cycle. What we know, the Carnot cycle is a unattainable ideal. It is a ideal cycle only. It cannot be attained in a real life situation. What can be the reason for that? That is, it is having this 4 to 1, that is a constant temperature heat addition process. Then immediately after this constant temperature process, it is coming the adiabatic compression process. Adiabatic compression process. So constant temperature process, it should be a very slow process. Constant temperature heat addition process. Then immediately followed by a adiabatic process, means it will be a heat, that is there should not be any heat loss or heat gain during this compression process, adiabatic process, which will be a very fast process. So immediately after a very slow process, we should carry out a very fast process, then again followed by a isothermal or a very slow process, again followed by a very fast process. So a practical case, it is very difficult to attain this Carnot cycle, which is having alternate very slow process and immediately following that very fast process. അങ്ങനെ ഒരു മെക്കാനിസം ഡിസൈൻ ചെയ്യാൻ വളരെ പാടാണ്. So we know that Carnot cycle is an unattainable ideal, but why we are discussing it? First of all, it is a standard for comparison because as we have discussed, Carnot cycle is the only cycle available to human beings which will be producing maximum efficiency or maximum effectiveness when working between two defined temperatures. Then it will be acting as a guide to the temperatures to be maintained for achieving maximum effectiveness. നമ്മൾ ഒരു ഏതൊക്കെ ടെമ്പറേച്ചറിലാണ് നമ്മുടെ റെഫ്രിജറേറ്റർ വർക്ക് ചെയ്യേണ്ടത് ഒരു മാക്സിമം എഫക്റ്റീവ്നെസ് പ്രൊഡ്യൂസ് ചെയ്യാൻ എന്നൊക്കെയുള്ള ഒരു ഐഡിയ തരാനും കൂടെ നമുക്ക് ഈ കാർനോട്ട് സൈക്കിൾ യൂസ് ചെയ്യാം. Then next we are going to discuss the coefficient of performance. Coefficient of performance. I think you might have heard about this term, coefficient of performance. Why we are discussing in this COP in our refrigeration and air conditioning? This is the case. That is, the term efficiency. The term efficiency is not used for refrigeration. Okay. For example, we mechanical engineers. First, we will be describing a system by means of a meaningful diagram like this. Then we will be discussing we'll be trying to draw it on our thermodynamic graph or any meaningful graph like that. Then what we are going to do is, then we will try to understand its efficiency or effectiveness. Okay. So we cannot use the term efficiency for refrigeration. Why? Because it is a misleading term. Because the term efficiency means output by input. But we know the output means, what is the output in our refrigerator working? So if you observe here, so the output means the heat is getting rejected. So the term, if we are using the term efficiency, we have to use the term output. But the term output here means the heat is getting rejected to the surroundings, or the heat is getting wasted. Means it is a we are if we are using the term efficiency, this it cannot be properly used for qualifying or qualification of our refrigerator. So we are trying to modify this term efficiency by some other parameter, by denoting some other term. So we are slowly modifying our term efficiency as coefficient of performance. So here ഒന്നുമില്ല, നമ്മുടെ ടേം എഫിഷ്യൻസിനെ നമ്മളൊന്ന് റെഫ്രിജറേഷൻ പർപ്പസിലേക്ക് നമ്മളൊന്ന് സ്യൂട്ടബിൾ ആയി നമ്മൾ ഡിഫൈൻ ചെയ്യുന്നു മാത്രം. സോ COP is nothing but magnitude of desired commodity. You please listen. Magnitude of desired commodity in place of output. In place of output, we are denoting it as desired. What is the desired output by the divided by what is the expense coming at our end, or what is the total expenditure in order to produce this desired output. Okay. So what is the desired commodity, or what is the desired output in our refrigeration? Useful refrigeration. എത്രത്തോളം കൂളിംഗ് എഫക്റ്റ്, എത്രത്തോളം റെഫ്രിജറേഷൻ എഫക്റ്റ് നമ്മുടെ റെഫ്രിജറേറ്റർ പ്രൊഡ്യൂസ് ചെയ്തു. സോ ദാറ്റ് ഈസ് കമ്മിങ് ഇൻ ദ ന്യൂമറേറ്റർ. So what will be coming in the denominator? What is the expenditure from our part as a human being operating the refrigerator? What is his expense? The net work done in order to produce the refrigeration. So the net work done will be coming in the denominator. Okay. So how we can denote this useful refrigeration using this TS diagram? We have already discussed in our TS diagram. Okay. So where is this refrigeration happening? The refrigeration is happening in 4 to 1. So 4 to 1 is represented over here. Okay. So how we can represent the net refrigeration or the useful refrigeration? Refrigeration means the heat addition happening in 4 to 1. Heat addition happening in 4 to 1. നമ്മളൊരു TS ഡയഗ്രത്തിൽ ഒരു 4 to 1 ഡയഗ്രം ഉണ്ടെങ്കിൽ, ഒരു TS ഡയഗ്രത്തിൽ how we can represent the heat getting added or removed, just multiply temperature with the entropy change. So the entropy change happening is S1 minus S4. S1 minus S4, because the cycle is moving from 4 to 1. So S1 minus S4 multiplied by the temperature. So temperature here we are assuming it as T1 and T4 are same. So here we are assuming it as T1. So T1 times S1 minus S4 is the refrigeration, or the heat getting the heat addition happening. Okay. Then comes the net work done. Net work done, here we are discussing about our Carnot refrigerator. So in a Carnot in a Carnot cycle, last class when we discussed about the Carnot heat engine, the net work done is nothing but the heat, the difference between heat absorbed and heat rejected. So heat rejected minus heat absorbed. Heat absorbed നമ്മൾ already കണ്ടു കഴിഞ്ഞു, T1 into S1 minus S4. So that is coming in the numerator also. Then what is the heat getting rejected? So now let us try to understand what is the heat getting rejected. Heat rejected to the surroundings is happening from 2 to 3. So the working fluid is moving from 2 to 3. Okay. So that 2 to 3 process is shown over here in the TS diagram 2 to 3. So the heat is getting rejected. So please, if you observe here, what will be the heat getting rejected? The temperature times the temperature here is T2 and T3 are same. So here we are assuming as T2 itself. Okay. So T2 times, what is the entropy change happening here? It is the working fluid is moving from 2 to 3. So S3 minus S2. Okay. So it will be S3 minus S2. So it will be S3 minus S2. Then so S3 minus S2. So it will be S3 minus S2. Okay. But what is happening here? Yes. So what is happening here? S3 minus S2. Okay. Then yeah. But here we are talking about a heat rejection process. So here we are talking about a heat rejection process. So what will be the final expression for S3 minus S2? So heat is getting rejected. So thermodynamically, heat rejection means the system